us, the workers there, had an open slot, the customer would walk up to. So
So
the next person in line, he came up to me. I pitched him the same thing. He said he was in a contract, and he said maybe in the future I'll think about it. So at the retail store, we're kind of told to make a list of people that may be interested in, signing up for the mobile plan and contact them, maybe down the line if they're interested. Within the next maybe month or two, I think I called them 3 times, like once every other 2 or 3 weeks. And on the first call, he was like, "Yeah, I'm
yeah,
still interested. I don't know if you remember, but I'm in a contract." The second time,
so I don't remember what the last thing I streamed was, but so we had a meeting with Mazda, and yeah, let's just say it went well. We presented the job navi. It wasn't really part. It wasn't the purpose of the meeting, but one of the HR ladies had prepped the room for the meeting, and we just showed it to her, and yeah, she liked it a lot. We got a lot of information. You know, what are like things to add, things to keep, things to change, sort of things. So yeah, like the CSV, sort of like the Excel style, the CSV style layout is really good, and she liked that. Um, yeah, I mean that's pretty much that. But yeah, other than that, so yeah, I don't actually know if I really explained what Clarkin is, but it's like a content marketing agency, right? So we create videos for, you know, in this case, we're creating videos for Mazda or for Hirojiran. Um, we're trying to bring traffic to Hiroshima, essentially. Trying to get, you know, trying to show to the world, well, to Japan, like, hey, Hiroshima has a lot of potential, a lot of opportunity. Come down here. You don't have to be in Tokyo. There's plenty of there are plenty open arms down here. And yeah, so we created this job, basically Hiroshima Job Navi project, which is to let people know what opportunities are here in Hiroshima. Obviously, there's Micron and there's Mazda, and there's like these what do you call them? Like iron mill companies, and I don't know. I'm still getting onboarded, to be honest. So I'm not so sure what there is, but there is opportunity in Hiroshima, and actually a lot of businesses are struggling right now because we're not getting enough people. So we're just trying to bring life back into Hiroshima. That's really that. But so Clark and we right, Clark and we also have our own problems. Like we don't have enough people. Um, we don't have enough money. Um, we need more time, but and like we need more time on our hands as well. And whatever sort of like we don't even have any productivity software. We're not using a Notion or a Slack. I mean, we are, but like we're we're not committed to it. So now we're trying to put in some rules, and you know trying to get people to we're trying to decide on like what are we going to use, what are we going to stick to, and what how are we going to fulfill our positions. And we're just trying to figure all this out. It is because currently the case is we don't know what the hell anyone is doing at any given point in time. We have Rudy and Taishi and me. Taishi is always has some on his hands. He's either emailing people, emailing Mazda, or the 27 other clients that he has, and or he's going to a meeting in Hiroshima City, or he's driving all the way to fucking Osaka for a meeting, just doing a lot of networking stuff, right? And on top of that, he's obviously facilitating the processes to his employees, right? Our peers, um, like, hey, what, making sure people are getting their fucking work done, right? And that's a lot. That's too much for one person. Um, so we're just trying to make. I'm currently working on a tool to leverage task management, um, right? Because essentially there's no task management right now. It's all kind of manually done. So I made this Discord bot that you can. It's just a task manager, like a consultant. I can be like, hey, I need Jeff to uh, finish XYZ project by next 4 days. You know, the whole point is we can provide the requirements in plain English or plain Japanese, and then the bot just parses it, and then it's added to its memory. So and then obviously I want it to remind people, you know, remind the fulfiller of the task when their time is running out, and it's sort of a accountability system, and just not really an accountability system. Well, yeah, an accountability system, and should hopefully get people to do their work. Not just that, but the main value point is that it's an offloading system, so we don't have to keep in our own memory. We don't have to create like these multi-threaded systems in our own brains. We just kind of offload it, right? So, um, yeah, like that's that, right?
I learned some new information, so I was like, hey,
Another thing is like
you can leave the contract.
another thing, right, is when we message clients um about like the whole correspondence between us and our clients when we're fulfilling these video creation tasks is until like that entire correspondence will happen until the video is done. So it's like a video can take a week to make. So you have a week of correspondence between you and the client. You're just saying like you're just updating them on the status. Like that's something that could be completely automated. There's no reason that you have to. It should just be a fire and forget. They want a video, you message them once with the link of where the video will be, and then they just get like notified or something. Even better than that, you just don't have to send any messages. Um, obviously, obviously it's like it's more professional to include a message. Like you gotta have some human interaction. I think human feeling interaction. I should say you need some human feeling interaction. So yeah, that's what Taishi is really. I think that's where he should. I mean, I don't know. Taishi shouldn't really be facilitating any of these things. We should have like a sales, not a sales, but I mean, it kind of is a sales, right? We need a communicator. Taishi should be like the navigator. We should have communicators. We got the navigator. We got the communicators. We got the programmers. I don't know. I don't know. But it should not be so sparse. Right now, it's very sparse. Actually, maybe it's fine if it's sparse, but it shouldn't be overlapping. There's a lot of overlapping rules right now, and that's just inefficient, right? It's we need to define some. I don't know if it's right to say define boundaries, right? Because it's not about needing boundaries. It's just that creating boundaries has a positive consequence that, or a side effect. The positive side effect of creating boundaries is that there is no overlap, and there is guarantee that people are fulfilling their domains, which is inherently efficient. But because things are separate, there's no cohesion. So there's actually a consequence. So what you actually want is what you really just want, right? Is everyone to know what everyone is doing. You don't want boundaries. It's fucking stupid. Because the more boundaries, the fucking less you can do actually. Um, but yeah. Anyways, we're gonna create this spot. So, I should say, ChatGPT is gonna create this bot. Claude is gonna create this bot for us, right? So, why are we not using Discord API? Oh, we are using it. Discord. Nice. Yeah, so we're creating this bot in Haskell because it is easy to reason about, in my opinion. I do not want this aliasing. I just want to disable it. Like I just want to disable aliasing. Um, is that what we call it, right? It's aliasing, right? Is aliasing in program. And when two or more names are referred to the same exact mark location. Yeah, I don't like this. This is like import aliasing. I don't like this. I really hate aliasing. It's like I don't know. There's what about okay, hold on. Is shadowing a form of aliasing? Right. B is an alias of A, right? Shadowing occurs when the variable in a script relieves name and shadowing is about name resolution, not shared memory. Name resolution. Right. Right. Mm. So it's not aliasing. Yeah, so can those flags be globally defined in a environment variable? Because if they can, I'll just do that. I don't want aliasing. What? Package? Yeah, I don't know. Cable. Is it called Cabal or Cable? Hmm. Oh, that's probably why the multi-threaded compilation isn't working. It's probably a cable. I don't know what it's called. Cabal flag. What the fuck is this? Hmm. Hmm. I want a single environment variable for disabling aliasing and enabling move type variables. Why couldn't this just be done by a single environment variable? Why there's so many fucking flags? No, it's really bullshit to me. I smell bullshit. I don't know. Um, hmm. Right. Hmm. Okay. Oh gosh.
If you pay off your phone early, if you pay off, he's like, yeah, I'll think about it. How about you call me back in like a week or something? So I did. I called him the next week. What he told me next, I was not prepared for because I did not believe what he was saying. He answered the phone. He's like, oh, yeah, I remember you. First things he asked me was, how much do I make in my current job? Immediately, the first thing that came to my head was, this guy is about to offer me an insane job. And this was all on the phone. I'm still at work, using the work telephone. So I told him approximately how much we make. He said, hey, I'm a manager at this company. I think that you would be a good fit. And, the earnings are above six figures, essentially. I was kind of freaking out. I was still at work though, so I had to be like cordial. I had to, like kind of tell him, hey, I'm at work. Let me give you a call after work. I got his phone number. I texted him because there's still a line of people, like customers behind him that I needed to help out. So I couldn't really be having this conversation right now. So first thing after work, I called him. I called him in the Uber going home, and I was just like, "Hey, what is this about?" He told me the company. It's essentially another sales company. A lot of people get the wrong idea when it comes to sales because they always think of like the sleazy car salesman or whatever. But this was sales for software, and I had no idea what I was getting myself into. He told me about the company. He said, "Look it up. Call me back in a couple days if you have any questions." It was essentially a healthcare company that sold software to like dental offices, chiropractors, things like that. Thing is, my auntie, she's actually in the healthcare field, so the first thing I did was ask her about it because I was super skeptical. Like, it doesn't feel real. Who just comes up to you at your work and offers you a six-figure job?
Oh
My
my god.
auntie told me that she's heard of the company, it's super legit, and she thinks that I should go for it. I thought about it for a while. It's like it's a big leap. I don't have any experience in this sales tech world and the dental world, to be quite honest. I was scared because I was doing pretty well at this cell phone job. I, felt pretty comfortable, and I was scared. Like, what if I don't do good at this new job? Like, will I regret leaving this good job that I have right now? He told me that training starts in 3 weeks, so I had 3 weeks to make up my mind. I thought about it for about a week or two. He also told me that the salary, I've never had a salary job ever. He told me that the salary paid more than what I was making hourly plus commission at my old job. I was like, wow, that is insane. For me to come from Taco Bell, making $10,000 a year to potentially $10,000 a month was mind blowing. I knew that if I didn't take this opportunity, I may not ever get it again. And the thing is, I asked my manager at my current job what his thoughts were. He said that he wouldn't blame me if I went for it. He was a little mad because, I came in and out of that job really fast. I was only there for about 2 months. I wouldn't say mad, but really fast. I was only there for about 2 months. I wouldn't say mad, but he's just like disappointed. I wrote out and chat GPT'd my resignation letter. I printed it out. I left it on his desk. And from there, I got hired at this new job. I'll have another video explaining why I quit. Probably think I'm crazy for quitting a 6-figure job, but it made sense to me. And that video will be linked in the description if you want to see why I quit my 6-figure job after working at Taco Bell. What you should really take away from this is if you get a job like this, don't give up. Like bottom of the barrel type of job, just don't give up. Keep applying to as many jobs as you can on your break, when you're at home. If you're like watching a YouTube video in the background, just apply to jobs. It's not hard to get a better job. And the whole time I was at Taco Bell, I was telling people about, everyone there kind of agreed like this job sucks. We all want something better. We'd complain about it. And, just from doing research for like 30 minutes, I think that In-N-Out pays like almost 50% more. Even Panda Express, they pay way more. Taco Bell is just like bottom of the barrel. And the thing is, I applied to almost every single Panda Express and In-N-Out in Las Vegas. I didn't get a response, but hey, the more you try, the higher chance is that you can get out of whatever you're stuck with. So just keep trying. A lot of people say it's hard to find jobs, which I kind of disagree with. I just feel like you have to try the spam method. Literally apply to any job. Even if you don't think that you'll get hired for it, just apply to it. You'll never know. And a lot of the times.
And now, a very special Black Friday episode.
Everyone hungry for
Interesting take. I think they're a little bit starstruck. That's the word. Money struck. But not fully agree.
Hello, everybody. Yeah, we have a good crowd for John's second talk. It's very exciting. This is the first year that John will be talking twice. A couple things to know. John will talk for about an hour or so, and then we'll have 30 minutes for questions. The mic is right there. That's actually just right there. And so just line up when we get to the questions. Try to keep your questions on what John talked about. If you get up and ask when Doom 4 is coming out, I'm going to kick you in the knee. So right there. I will not waste any more time, but you guys in the back, because John's going to write on the board, and we have plenty of empty seats here, you can file in. Don't worry that there's reserved seats there. Just go ahead and sit in them. All right, I will give you guys Mr. Carmack.
Okay, so I guess this is sort of going to be like a schoolroom session. I had deluded myself for a little while that this would be the first talk where I ever actually made slides to present, but it didn't actually come to pass, so it's going to be notes and talking and some scribbling on the board again. So almost all of what we do in game development is really more about artistry. It's about trying to appeal to people. But there's the small section of what goes into the games that's drawing the pictures on the screen that you can at least make some ties to the hardest of hard sciences. And while, it's great that people are researching the psychology and the different ways that people think about compulsion loops and some of these other game design topics, the raw physics that goes into rendering just kind of goes through the heart of physics, where it goes through the kind of the all-star list of physics with Newton's optics and Maxwell's equations and Einstein's relativity. And it's kind of neat to think that this is sort of brought to bear in the techniques that go into sort of making the games that we play. So at the start, you think, well, okay, we see light. So what actually is light? And we've got a definition now that light's the sliver of the electromagnetic spectrum that we can actually perceive. But that has a really long and complicated history for how we sort of reach that conclusion and how it's not really as clear-cut as most people would like it to be. Optical research started kind of all the way back with a lot of the Greek philosophers. But Newton did a whole lot of work with breaking light up with prisms, seeing how white light was actually composed of all the different colors of the spectrum, and they add together to make what we perceive as light. And then there was a centuries-long debate about whether light was a particle, like this little tiny billiard ball, these photons that you shoot out, or a wave effect, like all the things that you see in waves in water and waves in matter, so on. And finally, we reached the conclusion that, well, it's a wave-particle duality that quantum mechanics talks about. And this is very unsatisfying when you begin looking at this. But it's really pretty much irrefutable. There are these straightforward experiments that can be done to show that you look at it one way, it's a wave. You look at it another way, it's a light, or it's a particle. So luckily for computer graphics, we hardly care at all about that. Only when you start looking at some aspects of surface reflectance models do you start caring at all about some of these quantum mechanical properties of light. For the most part, we can look at light as zillions and zillions of little billiard balls shot out from lights and bouncing off of things and eventually reaching our eyes so that we can perceive them. There's a lot of simplifications that have to happen when you talk about simulating this. There's a lot of engineering disciplines like thermal management, radio engineering that do simulations of the electromagnetic spectrum, just other parts of it, how they bounce around, interact with things. And this is done all the time, and it works. It really is science. So you can say rendering an image or deciding how much light reaches a particular area is about as basic of a science as it comes. There's not any artistic measure in here. There are tons of other aspects once you get into perception that do become questions about, well, maybe there is artistry that goes into producing something when you've got an impression that you want. But when you're talking about simulating an environment, which most of what we do in sort of the hardcore FPS type games is we are pretending that we've got this virtual world and we're running a camera through it and we're trying to simulate what's happening in various ways. And nowadays, we know what we would have to do to make that almost perfect. We just have nowhere near the computing capacity to do really, really high-level simulations. But we can trace it's useful, even if you're not going to do the right thing, to at least understand what the right thing is and then understand which trade-offs you're making and make them with sort of a clear head rather than accidentally backing into trade-offs that may or may not be really the best way to go about things.
I need to figure out if
So
the place is open.
so many
I'm
that
hungry.
it took a long time for people to realize that
I'm
these other
very
phenomena,
hungry.
things like radio waves, and there's a lot of confusion in 19th and 20th century physics about like which things were particles and which things were rays, and we still have kind of mixed up terminology when you talk about cosmic rays that are actually particles, and you talk about alpha radiation and beta radiation and these things that are particle based rather than being rays from the electromagnetic spectrum. But we use this stuff all the time for radio waves. Your Wi-Fi has 2 gigahertz frequencies. The visible light rays are up in the terahertz range, many terahertz. But they're basically the same thing. They just differ in how they interact with matter. They're produced in somewhat similar ways, but the different things change. They behave differently when they interact with other things based on their wavelength, which is why X-rays can shoot through things, radio waves can go through some things that visible light pretty much bounces off of. So another important critical thing really is that photons, the little bundles of light that we talk about, they are absolutely quantized. It's again part of the quantum weirdness that you can't send off this arbitrarily divisible amount, but there is an almost unbelievably large number of them. Given light that's throwing out is, I can just say zillions with a straight face because it's a very large scientific notation number. It's not trillions, it's not quadrillions, it's even more than that are coming out in terms of these bundled little quanta of energy. Now, they do have characteristics to them. If we treat them as little billiard balls, in computer graphics, we are generally looking at only a few different spectrums, of a few different wavelengths in the spectrum of light. And that has to do with an aspect of the human visual system. While there are this incredibly divisible spectrum of light that goes out, we're only susceptible to 3 sort of styles of light, and they're not even individual frequencies. That's why we can get by with red, green, and blue for our monitor's emissive spectrums, because we only have 3 types of color receptors in our eyes. And I often think how it would be really interesting if you could look at all of these other spectrums bouncing around, and that's what thermal imaging and some of these other things let you sort of get a peek into it. And that's only light that's EM radiation that's very close to the visible spectrum, the infrared. It would be much more bizarre and interesting to be able to visualize radio waves in a real-time space, to like see all the multipath that's causing your Wi-Fi to be weird in specific ways.
Someone did that.
Moving
The
something
lower.
over here causes the radiation to change so much at your antenna to make a difference in your reception strength. And these are all things that have a bearing to what you do with light transport, as well as other wave phenomena like audio. Like really, really high-end audio processing is the exact same thing as what we treat light processing. You send out energy, it bounces off of all sorts of things in the world, and eventually arrives at something that's going to perceive it, which would be your ears in that case versus your eyes. So to kind of start with the path of a photon, of what it would take.
Nice, look at that.
You've got
So
something creates the photon, and for the longest time in our human existence, about the only thing that we saw creating photons was a great deal of heat. You heat things up hot enough, and photons start coming off of them. You heat it up enough, it starts glowing a dull red. You heat it up more, it starts getting more yellowish and towards white as more and more of the colors of the spectrum are emitted from these hot things. And obviously the sun is a very hot thing, where you've got a fusion reactor going, and the light that comes off of that is all of these atoms giving up some energy. So photons carry energy away from where they came from, and this is radiative heat transfer, where something gets hot. If you leave it all by itself there, it glows, and it eventually stops glowing. It cools down, going down through the spectrum, getting cooler and cooler until you don't see any visible light, because it's actually lost much of its heat. On Earth, radiative heat transfer is the least effective form of heat transfer. You get much more from conduction, where it just kind of goes through the actual physical contact into other areas as the heat spreads out, or convection, where moving currents of air or water take the heat away. But in space, radiation is the only way you lose heat. And in aerospace engineering, this is extremely important. Things like the areas like the International Space Station and spaceships, they have to worry a whole lot about thermal management, because the only tool they've really got is radiation. You see these enormous solar panels where they collect solar energy, but a lot of space vehicles have to have enormous radiators where they actually let the energy go out from the vehicle. Otherwise, they would get hotter and hotter. So it's important to note that even if it's not glowing so that we can see it, everything's still radiating. So you don't see the space station glowing red hot. It's just glowing at whatever its normal temperature is, which can be perceived with infrared sensors. But it slowly loses energy, and it eventually reaches a balance. That's why something stuck out in the sun in space doesn't get hotter and hotter. Eventually it reaches the point where the light that's coming in and hitting it is equaled by the radiation that's leaving it. And there are... we've made rocket engines that are radiatively cooled, where they burn 5,000 degrees or so inside, and they get so blindingly white hot on the outside that all of the energy that's not going out the nozzle, that's soaking into the walls, is radiated away as a whole lot of light. And this is essentially what old-style incandescent light bulbs were. You had a tungsten filament, you made it really hot by pushing electrons through it, and it got hot enough and it started glowing. And if you watched closely, if it was a heavy filament, you could watch it warm up or especially shut down. It would go through, kind of ramp through the temperatures. You would see it be red and get up to white hot, and then when you shut it down, it would cool down through yellow and then back through red before finally settling back to radiating in non-visible regions at sort of room temperature eventually. Nowadays, we have a lot more efficient ways to create photons with fluorescence and LEDs, things that are tuned carefully to just barely nudge the electrons in the atoms out to an excited state, let them collapse back down, and spit a photon out. For the most part, photon emission is random in terms of which direction it goes. When you look at radio engineering, there's huge bodies of literature for antenna design that determine how you can make it slightly stronger or weaker in different directions, but there's still a very fundamental nature of randomness, which is, again, the quantum mechanics aspect of things. There is, at a very low level, natural events are completely random, and you can't just say, I only want photons that are going to come out of the left side of this material. So you get a photon that pops off in some random direction. It may go straight for, if it's coming from a distant star, it could go straight for trillions of miles, more or less just traveling through space. There's little bits of general relativity with warping of light that can happen, but for the most part, it can continue on indefinitely. It's a self-propagating wave. So it pops off of some atom somewhere, maybe flies through space for 1 billion trillion miles or something, comes in, finally hits our Earth's atmosphere, and then starts interacting with the atmosphere in some way. Every change in density that visible light goes through will result in it bending its path somewhat. This is called refraction. The most obvious case when you look at it is things like prisms and lenses, where you can see the light really strongly warped. But it happens in any sort of density change, going from the vacuum of space to the outer reaches of our atmosphere, and then every change in pressure or temperature changes the density, and that causes very slight and subtle movements of the changes in the direction of the light. And this is actually why stars twinkle out at night. If you're on a clear night and you see stars coming in from billions or trillions of miles away,
A monad is a well-known concept in functional programming languages like Haskell. But what is it? Well, it's a monoid in the category of endofunctors that respect certain rules and has operations that chain computations together. This may sound like incomprehensible blabbering to you, but my goal is that by the end of this video, you know exactly what it means. I think it's important that we as programmers sometimes dive into the theory behind programming. It helps us gain a broader understanding of why things are as they are. It also helps us impress our loved ones at social events, assuming they're interested in category theory. This video has been on my list for a very long time. It's sort of become my nemesis. When I look online for explanations about what a monad actually is, it's often way too theoretical, using terms that are hard to understand for the average programmer, and without really diving into why this concept is useful. Today we're going to explore what exactly is a monad, and we're going to find out if monads are useful at all beyond functional languages like Haskell. Be warned though, I'm going to dive in pretty deep in this video. If you feel like it's going a bit too far, take a break and join my free Discord server at discord.iron.codes. It's a really nice, helpful community. Now, if you're ready, let's dive into the rabbit hole. A monad is one of the few design patterns in functional programming. Like I said in the beginning, a monad is a monoid in the category of endofunctors. What does that mean? Well, let's start at the end with the word endofunctor. And for that, I'm first going to look at the last part of that, which is functor. So what is a functor? A functor is a combination of two things. It's an object, a value, combined with a mechanism to do something with that value. Now, that all sounds rather abstract, but if you take a look at this class that I've written right here, this is an example of a functor. It has a value, which gets set in the initializer, and it has a mechanism to do something with that value, namely applying some sort of function to the value. So you see that's happening here in the body of this method called map. We're calling this function, we're providing it the value, that's the mechanism of doing something with the value, and then map returns another functor. So these are the parts that defines what a functor is. It encapsulates a value, it provides a mechanism for doing something with that value, in this case applying a function, and after doing that, it returns a new functor containing that process, that changed value. And that's exactly what you're seeing here. And map is a pretty common name for that. An endofunctor is a specific version of a functor that does exactly the same thing, except that when it returns a functor, it returns something that has the same shape as the original functor that the method was called on. And by shape, I mean that it's the same combination of the two things. It's the value plus the same method for applying an operation to the value. And in this case, the functor class is actually an example of an endofunctor because it returns a functor which has the same shape as the original functor. even though the value is different. So it's really about the structure. It's not about the value, not even the type. If you have a function that takes a value, let's say, of type integer and turns it into a string, then functor is still an endofunctor because it returns something that has the same shape. It has a value. We don't care about the structure of the value. We care about that it is a value. And it has the same method for doing something with that value, for modifying, for processing that value. So that's what an endofunctor is. Here I have an example of class that's not an endofunctor. So this is class string functor. It gets a value, stores that value, and then it has a map method, just like the original functor that I showed you. Also gets a function. But here, this doesn't return a string functor. It returns a list functor, which is another type of functor that gets a value that's stored in a list. So in this case, what we're doing is that we're changing the functor that it returns. It's not the same thing. So string functor, because it returns a list functor and not a string functor, is not an endofunctor. It's a regular functor. If we go back to the original functor class that I showed you, I've also added an example here. So we start with a functor containing the value 5. And then if I do map add1, so the add1 function gets an integer and returns an integer, and then I map that onto this particular functor, then g, the result of that map function, is also a functor instance. That's because map returns a functor. So the functor returns another instance of the functor. The second thing is that it preserves the structure. So g is an instance of functor. Structure is the same. Final rule of something being an endofunctor is that there is composition. So if we map add1 and then we map multiplied by 2, and we take a look at the value, then that's the same as mapping, simply applying these two functions in sequence directly. And if we get the value that way, it's also exactly the same. So composing various maps in sequence is the same as simply applying the function. That's the rule of composition. So to recap, a monad is a specific type of endofunctor. It encapsulates a value, it provides a mechanism for doing something with that value, and that mechanism maps back to the same category. So you start with a functor, you start with a monad, and you get another monad back as a result. It also preserves the structure, so you get the same monad back, and it preserves composition. So instead of mapping two things in sequence, you can also simply call those two things immediately, and then the result is going to be the same. So the monadness doesn't change composition. Another aspect of the monad is that it's also a monoid. So what is a monoid? Well, it's a set of elements with a binary operation. So you combine two elements that produces a third. It should be associative, so the order in which you do the binary operation shouldn't matter, and there should be an identity element. You should be able to pick one of the two elements as a particular value, and then it should result in the same element. If you take a look at this function, for example, that's of course a very basic function, but this is actually a monoid because it's a binary operation, so it takes two elements, returns a third, which is the sum of x and y. It's also associative because it doesn't matter if we do x plus y or y plus x. And there's also a unit element, 0, because if we add 0 to x, then we get x. So this is a monoid. And a monad is a monoid in the domain of endofunctors. So monad is an endofunctor, so it encapsulates a value. It provides a method for doing some computation on that value. And when it runs that computation, it returns another monad that has exactly the same structure. But because it's a monoid, it also has these two aspects of having a unit type operation and being associative. So here's an example of a monad, which is only slightly different from the functor example that we've seen before. So I have an initializer that gets a value. I have a map method. In this case, I'm calling that bind. And this simply applies a function to a value. But instead of turning the result of the function here into a monad, like what I did here, I turned it into a functor. So I'm not doing that here. Actually, here I'm expecting that the function is going to provide a monad already as a result. And then bind simply calls the function and then returns the result. We also have a unit mechanism. So we can take any value and we can turn it into a monad, well, simply by calling the initializer. You could even remove the static method because it's already there in the initializer. Now I did one thing here, which is that I use generics, so that if I have a monad like this, I can basically use it for any type that I like. So I define two type vars, t and u. Monad is a generic that relies on a type t, and there's an initializer, so we get a value of a type t, and then we have the bind method, which has a function that expects a value of t, and that then returns a monad of type u. So this also shows that this function doesn't necessarily have to return something that has the same value type. It can be a different type. And then finally, the unit static method takes any value and turns it into a monad. And now we have a monad. And since a monad is a monoid, it has to adhere to these rules of, on the one hand, identity. So this should be a unit or initializer method. That's what you see here. But also the associativity. So we should be able to bind functions in sequence, and that should give us the same result as applying those functions directly. So here I have a main function showing again how this works. So I've created now a monad with value 5, and then first I check for the identity, so you can do that on the left side and on the right side. So in this case, I'm binding the monad with a function that turns add1 of x into a monad, and the value of that is exactly the same as simply calling the function with the value 5. So that's the identity part. Right identity is the other way around. So if I do bind on the unit and then take the value from that, that should be the same as the monad value itself. So this checks for the identity. The second part is associativity. So I should be able to bind f, then bind g, and that should be the same as binding a function that binds the function and then binds g. It's all a bit complicated, and here you can see I added the assert to check this, but it looks a bit complicated because of course there's a bunch of lambda functions and monads, but when I run this you see that actually the values in the end are the same. So it doesn't output anything. In other words, these asserts, they pass. So again, this all looks a bit complicated, but the whole idea is that a monad is a combination of a value that's encapsulated plus a mechanism to changing the value, and it has certain properties. So when you do that processing on the value, you get back another monad of the same structure. And if you do multiple of these operations in sequence using the monad bind method, then that's the same as applying those operations directly on the value without using the monads. That's the associativity rule. And why is this important and useful? Well, because of all those rules surrounding monads, it means that you now can encapsulate side effects in a monad object, because we know that the structure stays the same. We know that we're not changing the way that the order of applying operations changes. So that means that we can capture side effects in the monad object, in the value that is part of the monad object. And that's the whole idea of a monad. By the way, if you like diving into more advanced features like decorators, context managers, other advanced features of Python, you might enjoy my next level Python course. To learn more about that, check the website below. Now we've seen a basic example of what a monad is. Why should we use that? What is that useful for? Well, a pretty common monad that you may encounter is the maybe monad. And the maybe monad is a variety of this very generic monad that I showed you just now. The specific thing that it does is that you can provide an optional value. So value can be none. And then the bind method, it has a function that takes a value of the type t, returns another monad, right? But then what it does is that it returns the monad if the value is none. Otherwise, it simply applies the function to the value, like with the original monad. So instead of the simple monad I had here, which just always applies the function, the maybe monad only does that if the value is not none. And that's actually quite useful because that allows us to make sure we only apply an operation to a value if the value.
I learned that ChatGPT works best with detailed prompts, but I hate typing them. So instead, I dictate them using WhisperFlow while walking.
Actually is valid, is not none. So here's an example of how you could use the maybe monad. So I have a safe divide function that divides x by y, and it returns a maybe monad type float. So what it does is if y equals 0, we can't divide by 0, obviously, so then we return maybe none. Else we return x divided by y as regular. And then what we can do is use the bind function to do safe divisions in sequence. So here is a result. Here's an example. I start with 10, then I divide by 0, which is not allowed, right? So that should return none, and then I divide by 2. When I run this, you see that the result is none. We don't get an exception or something like that. And that's because the maybe monad takes care of routing us to the non part of the monad whenever we are not able to divide by 0. So here, because I'm not able to divide by 0, that results in maybe none. And then this bind method call simply returns self and doesn't do the second function call. So it doesn't run this function actually, which is nice because now we will only run this function if the previous step was successful. So if I change this into a 2, and then I run the code again, you see we get 2.5. So we have 10 divided by 2 divided by 2. And I can also turn this into a 0, and then you'll see we'll also get none as a result because the second division wasn't possible. So that's the whole idea of the maybe monad. And this type of programming where we have these two options, we have the one path and we have the path where we're still dealing with a value, is also called railroad-oriented programming because we have these two tracks that our program is running on. In that sense, it's an alternative to the regular exception handling of Python, which works differently, right? With exception handling, well, we have our program, and then if there's an exception, there's a separate piece of control logic that you deal with, which is the exception handling part of your program. With monad, with the maybe monad, you have two paths, the non-path and the valid path. So it's a different approach to handling errors. And to show you how this all combines, so here I have another example, which is again the maybe monad, but I did things a bit differently. So I now used pattern matching, which is a new feature, relatively new feature in Python that allows me to do match case statements. In order to support this, I needed to extend the class a bit so that I tell the maybe monad that it should match arguments on the value, so that's what it should check. And then I also have a match dunder method that compares the two values of these two monads, the two maybe monads. Then in this example, I have a function that parses an integer. So we get a string value and it returns a maybe monad containing an integer. So if we can't turn it into an integer, then we simply return that. If there's a value error, we return maybe none. So this translates the Python exception model into a monadic error handling model. And then I have a few other functions. So one checks whether the value is positive, and here's another function that simply doubles the value. So then what we can do is again use the bind method in sequence. So we have some input string, and then we bind the various methods that we call in it. And since double doesn't return a maybe monad, it simply returns an integer, I have to turn it into a function that returns a maybe monad. So that's why the lambda function is here. And then when we have the main function, so I have my example input 5 minus 3 foo. So of course only this one should actually end up with a valid value, because here the value is not positive. So this is going to put us onto the non-path, and here foo is not an integer at all. So we should already go on the non-path here. And then because I added support for pattern matching to the maybe monads, I can now call this function on each input and then match the result and handle the different cases. So in case of maybe none, I say that it's invalid input. In case the value is an integer, I give this as a result. And in all the other cases, I simply provide default handling. So if I run this, then this is what we get. If we process 5, the result is 10. If we process minus 3, we get an invalid input minus 3. If we process foo, we also get invalid input. So the railroad programming here works. We don't get an exception because that's transformed into a monad. That's actually what happens here in parse int. And we either stay on the valid value path or we go to the non path. So this is how that works. The final thing you could do to make this a bit nicer is to create a decorator. So here I have a function called maybe that contains a wrapper function and then returns that wrapper as a result. This is a standard way in Python of setting up a decorator. And then it already contains the part that turns exceptions into the maybe monad. Now normally you shouldn't accept for the general exception type. You should always handle specific exceptions, but because here we're patching into the exception handling mechanism and we want to change how it works, I think it's allowed to do that. So what you see is we have a try. So we return maybe and call the function. And if there's an exception, then we return maybe none. So this does two things. It turns a regular function into a monadic function, a function that returns a maybe monad. And it also transforms any exceptions into maybe none. So that's really helpful. So if you have here, for example, the parse int value, so it returns a maybe int, we can now simply do it like this, have it return an int, and then we can throw away all of this code that we had here and use the maybe decorator. And now parseInt is a monadic function. And I did the same thing with the double functions. So now if we run this version of the code, we're going to get exactly the same result. But we really simplified things a lot by having this maybe decorator. So we can use our existing functions and simply turning into something that returns a maybe monad. All right, I feel like we've nerded out enough. Now, the question is, does this mean that we should now switch over completely to using monads in Python? Well, I'm not so sure. I mean, monads are typically integrated, directly integrated into the syntax of a language. You shouldn't have to be building this kind of boilerplate code. A great example of this is the Rust programming language. Actually, it has a maybe style monad, but it's called result. So Rust has this built in. Now, Python doesn't have a syntax like this for monads. We have to build it ourselves. Although there are libraries like the returns library that offers maybe monad. And you can use pattern matching to select which version of the track you're on. But especially if you're using a bunch of existing libraries, it's a bit of a pain to have to turn everything into a monad so that you're doing error handling the monadic way. So my conclusion is that at this moment in Python, it's not really a good idea to do this. But I do think it's good to know this type of programming exists, especially if you plan to work with languages like Rust in the future. But I'd like to know what you think. Would you use a maybe monad in your Python code to handle errors? Or do you prefer to stick with exceptions? Do you see other ways in which monads could help you write better Python code? Let me know in the comments. So I hope you enjoyed this video and gave you a better understanding of what a monad is, so that if you're at a party and a family member asks you, hey, do you know what a monad is? You say, it's a monoid in the category of endofunctors, and you actually know what you're saying. Now, there's lots of other aspects of functional programming that are interesting, especially if you look closer at the functools package in Python. And I did a video covering the functools package specifically. So if you like that kind of thing, you should definitely watch this video next. Thanks for watching, and see you soon.
Jesus Christ. Ew, what the fuck is
We
this?
have got to the point where literally anybody can build a fully working app without knowing how to code. This is
The code that you're seeing here works, but it's ugly, repetitive, verbose, totally un-Pythonic. Today, I'm going to take this pretty clunky fitness tracker script and refactor it step by step into clean, beautiful. I mean that I'm going to be using idiomatic syntax, classes, and expressiveness using features of Python that are really powerful, like comprehensions or generators. And it should feel natural in Python. Well, that's not very, and we can denote that by writing string or no, like so. With type annotate, it's also important that you don't forget about the return value. What's the result of a function? Here, that's also pretty straightforward. It doesn't return any result, so we simply write none. Logfoo doesn't return a value. And with log activity, we can do the same thing. So date, again, that's a string, or it's none. Calories burned, that's again a number. And the activity that we're logging, that's a string. Also, I'm not sure why there is an extra datetime import here. I'll just remove that. Finally, let's take a look at one day summary. So here also we have date. So that's also a string. There's also no return value here. It simply prints a summary.
I cannot watch this. Sorry.
It's going completely straight till it hits the upper atmosphere, and then it may slightly deviate, just tiny fractions of degrees, and this can cause the very small number of photons that you're seeing there to kind of come and go or move around in different ways. But the most important thing from a computer graphics standpoint are the effects that happen when it hits more solid matter, solid surfaces, or even liquid surfaces. And that's where it has the opportunity to generally, well, it can be even gas. You can wind up having the case of absorbing the photon. This happens rarely in gas. You can pass through hundreds of miles of atmosphere and not have too many of the photons absorbed. But it happens very rapidly in matter, in solid matter. A typical photon, when it hits a surface, might penetrate a little bit into it. A surface like metal will bounce off of just the first several atoms. It doesn't take many molecules or many atoms of metal before you can reflect light out, which is why you can make these super enormous space mirrors that are just a very tiny sputtering of aluminum on some plastic film, and they can actually make solar sails or giant solar collectors and concentrators. But for most other materials, the light can penetrate a little bit further into it. As it interacts with the molecules, it can either be absorbed, raising the temperature a little bit, going into eventually making it hotter so that it starts radiating out at some level, or it can redirect the photon in some way. You've got the minor redirections from the refraction, and much stronger ones when it interacts and bounces off of a solid surface. Now, there's a ton of different names. There's literally a couple dozen different names for the different ways that light can interact with surfaces. There's all the different types of scattering, of course, reflection, refraction. Reflection can be split up into specular reflection, diffuse reflection, and there's all sorts of different subcategories. I mean, optics is a huge topic. There are societies dedicated to every aspect of it, and there's huge terminologies for all of it. But for the most part, you can say photon comes in. If it's not absorbed, it's going to be kicked out some other direction, and then it can go and interact potentially with the atmosphere or potentially with another surface. And eventually, it's either absorbed, well, eventually it is absorbed somewhere, but for the most part, they're absorbed into the surfaces around us. But a tiny, tiny fraction of all the photons that are bouncing around eventually hits our eyes. And even when it gets to our eyes, which are mostly transparent, there's this chance that the photon hits and it specularly reflects off of our eye. And, it made it all the way out of the billions of possible traces, made it to my eye, and then decides to specularly reflect off some other direction. But most of it that hits the eye and hits the lens gets through, propagates through vitreous and aqueous humor and all the little biological parts of the eye, and hits receptors in the back of our eyeballs that turn those eventually into neural impulses that our brain works with. Now, our eyes can actually be quite sensitive. The rods, the non-color sensitive part of our eyes, when they're fully dark adapted, if you've been staying outside for in a dark area for 20, 30 minutes, single photons can cause chemical reactions to happen in the, inside the rod cells. It takes a handful of them, a couple dozen, for it to turn into a neural impulse. But it is possible for people that, especially in the old days, people watching for things on ships in moonless nights that might be out all night with nothing but faint starlight, you can have cases of just handfuls of photons coming off of something, being registered and showing up, and people acknowledging their existence, which is pretty amazing when you think about these incredible subatomic particles, not even particles, but incredible, the scope of that being detectable by us as biological entities. And there are limits to what you can wind up detecting with light. The visible light that we see has a wavelength, and you can't really deal with things that are smaller than that, which is why you're never going to have a real picture of an atom or a molecule, because those are much, much smaller than the wavelengths of light. You eventually use electron microscopes and then scanning tunneling microscopes and these other things that don't deal with light at all to take those super tiny pictures, like the Boy and His Atom movie that IBM Research did, which was done with a little raster grid of atoms, which is really, in the fundamental sense of the word, deeply awesome, that we are dealing with matter, the very constituents of everything at that level, and we can make a little movie out of it. But those pictures have nothing to do with light, nothing to do with rendering, and basically the techniques that I'm talking about here. That's a completely different way of sensing what's going on at that level. So to recap the basic pictures of this, you've got a sun up here, spits out some light, travels through space, gets to the atmosphere on the Earth, maybe bends a little bit, maybe just goes straight through, comes down, hits a surface, maybe gets absorbed, maybe hits something else. You've got walls and rooms and bouncing around in there, and eventually, if we're seeing it, reaches somebody's eyeball inside. And that's the physics of what happens. It's really well understood. It does come down to a lot of data acquisition and characterization. When you talk about how the critical interactions with the surfaces, when you've got your basic theoretical thing, if you talk about a flat surface, you say light comes in, what happens to it? That's the question of surface response. If you have a perfect mirror, and it's worth noting that you don't have to be perfect on an atomic level to be a perfect mirror. You only have to be perfect at the optical level, which is somewhat larger. So people can make basically perfect mirrors, just highly, highly polished things. A perfect mirror will have the photon reflect off in this exact reflection. If you take the normal to the surface, you wind up with equal angles there. So highly polished surfaces act like this. When you get a reflection off of something like the surface of water, it'll behave like this. But most of the surfaces that we look around us do not behave like this. We have a spread of the energy where it comes in and it bounces off to some degree in every direction. No matter which way you look at most surfaces, you see, again, zillions of photons coming in. Some of them go in every direction. They just go in a direction that's biased based on the type of surface that it is. A surface that, one of the easy things that a lot of times is approximated, both in the engineering sciences and in computer graphics, is to assume that the surface reflects perfectly diffusely, or it's a Lambertian surface. And what that means is that no matter which way the light comes in, if it hits it completely edge on, completely straight on, it has an equal probability of going in every direction. And there are some materials that are close to this. If you take something like a block of chalk, white chalk, that behaves almost as a perfect diffuse reflector. If you light it from one position and you look at that like a little scribed out area on it from any different area around it, it will appear to have about the same amount of energy coming out of it. But there are, all surfaces are more complex than that though. Most of them will say, if you've got light coming in here, there will be more of it coming out around the reflection area, and some general amount coming out in all different directions. But these can actually get quite complicated. And the simplifications that we use in graphics sort of approximate these, but you can measure these with specific tools that go in and take lots of samples from moving the lights around, because it depends. Unfortunately, this is one of the areas where it does get not so great for computer graphics. It depends both on the incoming direction and the outcoming direction. And those are two angles in each one, so it winds up being a four-dimensional equation to say how light comes in here, how does it come out in some other direction. And in fact, it gets worse than that, because very few things do reflect just off of this upper surface. Most of the time, the light will go in, go below the surface, bounce around a little bit, and shoot out some other direction. So if you're saying, well, my photon comes in here, not only do you have to say, if you're being really, really accurate, which angle does it come off of, but also how far away from the original point does it come off of? Or if it's a thin surface, how does it come out on the backside? You may have other setups coming there. When you look at like a leaf in the sunshine, you've got a lot of the energy bounces off the shiny top face, but a lot of it diffuses through and comes out on the backside. So these are not pleasantly analytically tractable things. They wind up being big tables of data. And one thing that's important to remember is when you see like tables of data that are collected for things, don't necessarily capture all of the important characteristics of a surface. Where if you take one of these sensors that you can capture a table of data here, if you did have your perfect mirror reflector, it's almost certainly not going to have the exact sample exactly where you want. But eventually data does win. Just as we increase resolution on things, we'll have higher and higher resolutions for our surface models. And we'll get closer and closer to reality for what we're simulating. So to go as kind of a capsule history of computer graphics rendering then, when computer graphics started off, if you look in the 60s and early 70s, computer graphics research focused on the hidden line problem. We had line-oriented displays, either true vector displays where, like the old video game arcade games like, I'm blanking out now. Yeah, like Asteroids is the best example, that are actually drawn by raster beams moving around where they really are true line displays. There's no raster, there's no edge aliasing, and all the different games like that were what the earliest computer graphics systems were basically like that, where they were vector displays. And once people learned how to draw, figured out all the basic projective math to say, all right, I've got my cube here. I want it to look like that, but when I draw it, I've got that on there. How do we figure out which lines that we're going to erase? And that was, that occupied research for a while to figure out effective ways to do that without spending at the time the scary divide costs for different things, and you'd have lots of interesting work going on. But when we eventually got raster displays where we could fill them in, of course, at that point, people filled in the surfaces of the cube. They're all grayscale at that time, so you can draw a cube and say, well, this will be the light face, this will be the dark face. But that was neat at the time, but that was not sort of what things look like in reality. So people started taking the steps that they could to try and say, what do we need to do to make this more approximate what we see with our eyes? And this has been a path that's been driven probably more than half by sort of ad hoc approaches about just, well, what's reasonably easy for us to do that gets us somewhat closer to it, while there's also been sort of a parallel path of saying, well, what's the physics actually doing? How do we make an actual solution for it? So the earliest things that got added to the shading model for computer graphics was, if we assume that there's going to be a light that's at some point, in the beginning, it wouldn't even be local. You just say light is coming in from this direction. So we want to be able to say what color or what shade should each individual surface be based on where that light is. So you've got the obvious things that if it's not facing the light, no light hits it, and you would draw it black. So the question about things that are directly facing the light, so if you've got light coming in, if you have a surface completely perpendicular to it, you make that your brightest color. If you've got a surface that's completely parallel with it, it gets no light, you make that 0. So you've got some curve that goes between it to say how bright something should be. And it turns out that that's a fairly straightforward bit of math to solve, where you have light coming in at a certain angle, you've got the normal to the surface. The amount of light that would strike a little surface there is proportional to the cosine of this angle. And that's not an approximation, that's actually a bit of ground truth. If you've got the light coming in and you've got something coming in at this angle, a surface that's, let's see, if you count the number of rays that go in on something catching 4 of them directly, turning it down only covering two spaces there. All that actually works out correct, and this is the basis for a lot of the real calculations for light transport. Not a hack, actually part of real proper physics measuring. So once you've got that basic approach, you go back to your cube, and you get your light coming in, and you've got a brighter face, a darker face, and the faces away from it are completely black. And then most people say, well, we don't usually see things like that. So now we get into the fudging, and you say, well, let's just brighten everything up a little bit. We'll add an ambient term. So you sort of just add this minimum level to everything on the back side. And that helps a little bit. If you've got a cube, then everything looks pretty much great because it's a constant color just on the side that you might not see over there. But if you've got something more complex, everything that's not facing away from the light winds up being the same color. And it's clearly not correct. It's not what you'd like, but it was all that seemed reasonable to do at the time. The next step was to start looking at surfaces that are more than these perfectly diffuse reflectors. If you model your cube like this, it looks kind of like it was maybe carved out of chalk. And it can be a decent representation of that. But very few of the surfaces that we see around us are really that simple. Most things have some kind of a shine or highlight on them. You know, as we look around, you can see reflections and highlights on all sorts of things. And the obvious bits of metal and plastic, little things that you might hold in your hand. I can look at all these different shines and reflections on the plastic that I'm holding here. Now, the observation was made that the highlights on most objects that weren't completely mirrors, they tended to be something like a bright hot spot, like if you had your sphere here, you would have a bright hot spot that kind of faded a little bit around there. And just by looking at that and saying, well, you know, what could we do that would be kind of like that? The observation was made that, well, if you take this sort of cosine arrangement here, this makes this nice broad fall off. It makes over the entire surface of the sphere, coming from that, it'll fade off till halfway around the light. But if you wanted something that was really tight, the thought was, well, we can just take this value and raise it to a higher power. We can just take this and go, square it, cube it, take it to the 20th power, which can be done, effectively mathematically quite cheaply. This has no basis in physical reality at all. This is a completely ad hoc approach, but it worked out okay. And this is what the Phong lighting model was about, where you separate it into your diffuse lighting, which is more or less what color the surface is, and then your specular lighting, which is what the highlights are going to look like. So you had this other value to play around with, and that was the specular power. And nowadays, I regret using that in my terminology, where we have power maps and nobody understands what those are. They relate to the specular exponent, what you're going to take something to a power of to tighten it. The better terminology that's used more often now is a roughness map, where you have a mapping, and you also do it in logarithmic space rather than linear, but more or less that's still today what a lot of graphics involves, is you've got a roughness parameter which affects this exponent that you take this extra vector to generate your specular highlights for. And again, it would make, so if you're rendering your cube and you get the light at the right angle, like if I'm looking at this here and the light's over here, it hits that. If that's at that right reflection angle, then you'll get a nice bright shade on there. That flat surface will catch the light and it will glint at you, and that would be looked at as a real advance for the rendering. So you've got something that looks diffuse, but when it moves into the light, it kind of catches a flash of light and fades out. So the facets on these solid shaded models started looking better. Now, what the next thing that people wanted to do is, okay, we've got enough cubes and tetrahedrons and dodecahedrons and whatever, so we want to start making things that look more realistic. We need to have a teapot. We need to have a curved surface in some way. So you make some curved surface like this. There was a lot of work in the early days on directly rasterizing curved surfaces, drawing them directly, but all the real-time graphics, almost all of it, has been a matter of turning your curved surfaces into approximations with flat surfaces. So you've got something that is theoretically a curve, but really it's a bunch of facets. So if you apply the lighting model there to it, you see all of these facets. It stands out as like, okay, you've carved this out with all these flat planes, and it doesn't fool you into thinking that this is this smooth curved object. So the next step in graphics that went on was adding the interpolation across across the vertexes, where instead of calculating a value for a face, you calculate it for a given vertex, for one corner, and then you just average. You interpolate across there so that a point here is going to be some average between 3 or 4 of the points that make it up. And that works surprisingly well. If you're looking again at a diffuse surface, it works out just about as good as you'd like. There are some minor artifacts called Mach bands that you get if it changes too much, but if your tessellation's okay, that works out all right. It works out less well with the specular highlights. And the reason is that your specular highlight, if you've got, it might show up, like if you were supposed to have some hot spot right here in the middle of a surface, if you calculate it at the outside, this is going to be almost 0 for the specular, almost 0. And when you interpolate across it, it's going to have nothing. You're just not going to see it. You'll only see a highlight when the specular comes up at the very edges. And this is what still to this day sort of the standard OpenGL shading model is. It's gross shading with calculations at the vertexes, interpolating the colors or parameters across it. So this model is still with us to this day for a lot of sort of quick stuff that's not visual simulation oriented. If you just write something using lighting with OpenGL, that's the model that you get if you turn on specular highlights. In graphics where they care more about visual quality, what started happening was interpolating not the color across it, but interpolating the normal, sort of the curvature across each point, and then applying the lighting model at every pixel. And at the time, this was like a flagrant use of processing power, because we're like, okay, these calculations are expensive. We have to do these distance calculations, dot products, exponential power stuff. And when you just do it at each vertex on your cube, okay, so you've got a handful of vertexes that you need to calculate. But even on an old school display, you would have hundreds of thousands of pixels. And so if you're drawing that there, going from doing this maybe a few hundred times or a few thousand times to hundreds of thousands of times for a scene was a large use of additional processing power. But it got you the good-looking areas where you could have a highlight that looked about like it should, moving across the surface, or sitting on a floor, looking stable there as you moved around. People that have been following PC graphics for the last couple decades, we've seen games that that do not have interpolation, the different ways where the lighting would change dramatically. We always had the problem of densely tessellated characters or objects and then very low tessellation on the world. And the problem that you'd run into with that is that if you're applying one of these interpolation schemes to it, you would have something that you could never have highlights in the middle of a surface, only at the corners. And there were also issues with perspective math and clipping that would mean that it would change as a really big polygon get clipped by the edge of the screen in almost all cases the way people did it. And this was one of the big things that pushed me during the Quake time frame to use light maps for the first time, where instead of, I had seen other games that were doing lighting at the vertexes, and I didn't think it was, it wasn't good enough. You couldn't get anything resembling a shadow. You had all these swimming artifacts with the lighting, and it just didn't give the, what I wanted to see. And while Quake didn't have any specular highlights, it did have you had samples every 16 pixels in the light maps that we interpolated across those, and that gave us the look that was very important for it. And we didn't get to actually, it was only all the way up to Doom 3 where we would start doing per pixel operations like this to get the much better calculations. So even with this level of graphics at that time, where you've just got sort of these Phong lighting, simple models, hacks like the specular exponent and the ambient term, we started to see some offline things being rendered like some movies. Early work, some of the early NASA promotional work that Jim Blinn did were significant in the sort of growth of all of this. And then we finally saw some feature theatrical films with like The Last Starfighter and especially Tron, where you would see, you go back and you look at Tron and you have a lot of these sort of Garo-shaded, solid modeled things on there with your light cycles or recognizers and so on. And they were doing something, they were intelligently picking a battle that could be won at the time. If you said, well, we have to go ahead and render photorealistic humans, we were nowhere close to up to that task. But we could do geometric solid models that looked good enough to show on the big screen, and that was a pretty big breakthrough. And simultaneously with this, there was an alternate approach to the way graphics were being drawn. So most of the early graphics were done with rasterization, where if you've got your computer screen and you've got your quad on here, you would draw this on a computer by calculating these equations of the lines, and then you would usually just kind of walk across, building up your rows of pixels. The whole process of hidden surface removal is another step on top of this, where if you've got lots of cubes, how do you know which one draws on top of the other one? And this was another thing, if you look back in research from the 70s especially, there was tons of work going on hidden surface removal of these clever different algorithmic ways. Today we just kill it with a depth buffer. We just throw megabytes and megabytes of memory and the problem gets solved much, much easier. But this path of rasterization is still with us today. GPUs don't rasterize in scanline order like this. They follow crazy winding paths to maximize memory bandwidth, to fill up tiles, to rasterize them in different pieces, and they rasterize all quads at a time. But it's still essentially a rasterization method where we have shapes and we figure out how to rasterize them. We figure out which pixels they're going to cover, and then we figure out what we want to do to them. The alternate scheme, which was also developed in the later 70s, is ray tracing, where instead of saying, all right, I'm starting with my object, I'm going to take these vertexes, these 4 vertexes that are in space, I'm going to take my virtual camera, and I'm going to transform them and find out where they are on the screen and then fill them in. Ray tracing goes the other way, where you start off with your camera in space somewhere and your little virtual viewing screen, and through that, you send rays out into your world and you intersect them with your cube over here. And if it hits that cube first, it knows it didn't hit anything behind that. It's got a surface point there, and it can apply whatever shading model it needs to. The thing that ray tracing gave, it's radically slower, like hundreds or thousands of times slower than rasterization if you're doing just the most straightforward thing. If you just want to draw that cube, you can draw the same thing with rasterization or ray tracing. It's just going to be 1,000 times slower with ray tracing. But it allowed a couple things that were either very difficult or impossible to do properly with rasterization. And the thing that you would always see in ray tracing demos is your shiny reflective spheres. So you've got a little chrome ball, and the fact that you could see the world reflected into it and then back into your eye was the thing that ray tracing could do that rasterization couldn't do really worth a damn at all. You would approximate it with environment maps and different things, but for reflections and for refraction, doing those things properly, ray tracing was really the only good solution. But it wasn't practical even for most offline work. I can remember looking at old research papers of things that are run on DEC-VAX computers, and they talk about the number of hours to render these really trivial scenes, just a few boxes and maybe a sphere sitting there. And the idea of rendering like complete worlds with it was fantasy at the time. But it did address some of those problems for the first time with reflection and refraction. And it also much more elegantly solved shadows, which all of this stuff talking about surface interactions and finding out what you hit with the light, that kind of dodges one of the really hard problems, which is saying that, well, the light obviously doesn't reach through things. If you transform something up here and you transform another surface down here and the light's up here, this should be in shadow because it's blocked by this. But that turns out to not be a particularly trivial thing to resolve. It's basically the same problem of how you view something from your point of view, but viewed from the light's point of view. And that can mean that, well, if every light in your scene has to do similar rendering process to what your view does, possibly harder because they're omnidirectional lights in many different cases, and it's just a tough problem. And as with so many things, there's a lot of wonderful research in the 70s and 80s going through about how you do shadows effectively with these different analytic solutions. In the end, we had a brief period where stencil volumes were an effective way to do things, but now it's essentially all shadow buffers, where we really do take every light, render an image from their scene, and use that to back project onto there to figure things out. But that was one thing that ray tracing had an elegant solution for. Again, if you're already 1,000 times slower, who cares if you're another factor of 2 or 3 slower? For every point you hit, you go ahead and say, I've got my light up here. I'll trace to the light or to however many lights I've got, and if there's something that blocks it, then that's going to be shadowed, and I can take it out. So ray tracing always had this much clearer abstraction of what you're doing. It's easy to tell that you're sending out a little array, you hit something, you determine whether you hit all of the other lights or if you bounce or refract into something else. So it's always been easy and clear. It's just had this 1,000 times slower problem to deal with. So the advances that were being made on graphics kind of after this early age focused on the changes in what you can do with the surfaces as the first obvious thing. And a lot of these were driven by sort of artistic and aesthetic concerns, where we got, if you pull up a 3D rendering program and you look at their material stuff, there's a whole page full of options, things that you can tweak, knobs you can turn, checkboxes you can set. And each of these had some use case where somebody wanted this because it made their image generally look a certain way that they wanted. Very rarely were these things driven by sort of physically correct rendering. And there was a huge plethora of these things that came out. Every different program had a different set of options. You always had this fallback of you've got your diffuse colors, your specular color, your roughness. This basic Phong shading model persists to this day, but now we have a ton of other things that we can tag on there, things that are subsurface scattering approximations, Fresnel lighting, different frequency response on surfaces. It's like some of the things do have physical basis to them. Like one obvious thing, the Fresnel effect is the effect that as you get more and more glancing to something, the reflection gets stronger and stronger. And you see this is what makes water and glass look like water and glass. If you look straight at them, you pretty much see straight through them without a whole lot of reflection. But as you get more and more edge on, even a surface like this, where when I'm looking at this angle here, I've got a very, very strong, clear sense of the slightly wavy reflection of that white line there, while if I look at it right here, it's barely visible. So that's a physical effect in reality that you can work through the real physics equations of why this happens, but people again sort of called up the trusty raise a cosine to a power, and it sort of looks like what we want when we're dotting a couple vectors together. So that's something that's based off of plausible physics, but generally only roughly approximated. And there are other things like that with like the change in some metals get their metallic look because they slightly change colors as they get towards grazing angles. So again, you can calculate the real physics for that, or you can just kind of say, well, this color sort of changes to this color at the edges and start interpolating between them. But lots and lots of good work and lots of high budget movies and so on were built with these sort of very ad hoc techniques. But sort of in parallel with this, the other big revolution that was happening was global light transport and global illumination. It comes back to that whole hack of the ambient term, this sense that obviously if I'm right here, the lights are only directly hitting the outside. The back of my hand has no direct view to any light, but it's still quite bright and clearly illuminated. It's bright because all those lights hit this whiteboard, bounce off of that, and wind up lighting my hand from the back. And you can see like color changes, like if I move up here where it's mostly covered by the blue marker on there, there'll be blue tints to it. And this recognition that so much of what we consider important in the visual field is actually indirect. It's not just a matter of here's the light, here's the surface, what's the reaction? Because we come back to how much of the light gets bounced around. And there's a term called the albedo of a surface, which is what fraction of the light gets reflected versus absorbed. And there's some tricky terminology with this because you can have either the total solar albedo, where you talk about how much energy comes off of the sun, and this is used for climate modeling and some remote imaging and things like this where you matter. But you've also then got the visible albedo, which for rendering is what we care about. And the point is that the best reflectors, your chrome sphere that's mirrored or your white piece of chalk or your freshly driven snow, those can reflect 90-ish% of the light, while your darkest surfaces, your lump of black coal or asphalt in some cases, might only reflect 5%. But when you're reflecting 90% of the light, what that means is that if you're in a room that has mostly white surfaces, a single bit of light coming out of your light emitter might bounce around a dozen times before it finally gets absorbed. So it could take a very complex path before it winds up getting to your eye. And this is why we could have cases like a dark room illuminated only through the crack under the door, but you can still wind up looking around, even around corners. You can go into the closet in the dark room illuminated under the keyhole and still find things somewhat lit. And that's because of this many bouncing path that light can take from the light emitter coming around till it actually gets to your eye. And this turns out to be a really frighteningly complex and expensive problem to solve properly. The first sets of attempts at this dealt with radiosity approaches. And a lot of this was driven by engineering things beyond just making pictures, because you would talk about things like heat management. If you have a certain amount of energy coming in here, how hot is something going to get, and what's the hottest part going to be, because that matters for a lot of engineering terms. So you can do things like, make a complex surface here and say, energy is coming in here. How much of this energy makes its way to here, to here, to here, here? And it's not just a matter of that's basic geometry calculations to say how much of this is directly impinging on that surface. What gets complicated then is you say, well, this reflects 50% of its light, and that 50% goes to all of these different ones here. And this one reflects 50%, and that goes to all the ones here. And in theory, if you're doing everything floating point math, you can keep saying, you can bounce it 100 times and say you get, 0.00001% winds up coming back to another spot. At some point, you just say it's converged well enough, the solution is not going to change much on no matter how many more bounces that you do. So the radiosity solutions work by creating this giant linear algebra matrix of coefficients, where you say, you identify all of your surfaces and you say what form factor, what fraction of the energy goes to all of the other different surfaces. And then you may be solving this 10,000 by 10,000 matrix. And there was a lot of work on the optimizations that go into solving this more effectively. But there are two reasons why radiosity is not a particularly relevant technique for computer graphics anymore. One aspect that it sort of glossed over was the notion of occlusion, where if you've got a surface, if this goes out here and you go around the dark corner, all right, we've got this surface here. It's clear that it can't see this surface at all. It can see this surface, it can see part of this surface, a fraction of it, and it can see an even smaller part of this surface over here. So you have to calculate these occlusion terms where you're saying each surface, unless you're in your deformed stretched icosahedron or some surface, some solid that has no concavities inside it, you're going to have these aspects of occlusion. And this becomes a very, very difficult thing to solve completely analytically. If you're trying to stay in just analytic world, and you try to solve, we have this surface occluding this surface, and then another surface here and another surface here. It's the potentially visible set problem on every polygon, and it's an analytic nightmare. So you wind up solving this by approximating. You just say, all right, I've got a surface here. I'll throw a bunch of rays to test out here, and I'll throw 20 rays out, and if 10 of them get through, I'll say I'm 50% occluded. Now, a purist will start blanching and saying, well, yeah, but that's random. There's this randomness. You might be misestimating. There could be pathological cases. And there's some truth to that. Anytime that you're sampling things, there are sampling cases that can turn out pathological. But the other side of that then goes, it's like, we're tracing rays. We have another technique that involves lots of tracing rays and come about it from the different route, which is to say, well, let's start with ray tracing and let's try and solve the global illumination problem using nothing but ray tracing, which leads to path tracing. So you could make a rendering solution, a rendering program where you start with your light emitter. You throw photons out in all directions. You have your cube here, and somewhere you have your eye. You will get a physically accurate image if you throw random rays, pick a random direction. It goes down, some of them go off here, some of them go up here, but eventually some of them wind up hitting a surface. And then based on what that surface is, you determine which direction the light goes out. It's going to be random. And again, your perfect reflector would not be random. It would go off in exactly the perfect reflection direction. All other materials will throw light in essentially all directions, but with different distributions. They'll be more biased towards the reflection direction. There'll be a chance that they go everywhere. So one of your billions of light rays goes out, hits there. It decides it's going to reflect up. Another one goes out, hits here. It's going to reflect over. But eventually, some ray is going to come down, hit a point here, and then reflect at exactly the direction that goes over and hits the surface of your eye, which the lens can then focus into something that you can perceive. And this has an interesting biological side to it. The larger an eye is, the more light it can collect, which is why animals that will generally hunt at night can have larger eyes, larger openings into their eye, and why telescopes get bigger to see more. This is what's happening in reality. Zillions and zillions of photons come off, they bounce around, and eventually some tiny fraction of them hit the lens of your eye or your detector or whatever you're using and can be resolved into an image. So you can make an image like this. People have done it. It is extraordinarily inefficient, but you can solve everything with it. This is a complete and accurate solution, as accurate as your analysis of what the light's distribution is and what the surface's distributions are. This can be as good as that. You can have your extra surface up here where you hit the ceiling, you bounce back down, you hit a wall over here, you bounce back over, and then eventually make your way to the eye. And you start thinking, well, you can have 10 bounces going in a random direction, your eye is only some handful of millimeters across, but you're projecting an area this size. How many traces do you have to do? Well, you have to do billions and billions, and you wind up with a very noisy image at that. But if you did enough of them, this would come out with the right solution. Trace array, it either gets absorbed or it reflects into a different way or transmits through it. You've got this whole, the model that you use, the bidirectional subsurface scattering distribution function. So as accurate as that is, determines what happens to the lights. You can have models of the lights. There are these standards like IES light tables that have, those particular lights. You could look up what's the distribution of photons that come off of them. You could look it up for all the different ones. And as good as the data is, your simulation can be as good as what you feed it. But it's hopelessly inefficient. What we wind up doing in different ways that can be reasonable approximations are, instead of throwing rays out from the light, which are mostly going to go nowhere near what you want, you can reverse the trace and go from your eye, like in the kind of classic ray tracing, go to the surface, and then you start getting into the cases where one of the sort of buzzwords in high-end rendering is whether a renderer is biased or unbiased. A biased renderer is not necessarily perfect physics, but they do it because it's going to be a lot faster. Like the standard thing that you do, if you don't mind being a biased renderer, is you say, well, I have all these directions that I could go to the world. I could go up to the ceiling, I could go down to the floor, but I know I've got all of these lights up here, so I'm going to send most of my rays towards the lights because those are almost certainly going to be the things that really make a difference. So you hit your point, and you say trace against every light. You've got 3 lights going here. Let's run a trace up against them, check for occluders, solid things blocking it off. And then you start throwing random amounts of rays in different directions. you can be smart and base it on what the character of the surface is. It again comes down to these distribution functions where you could have rays where it's more likely that if light comes in this way, it's more likely that it's going to make it out towards your eye, so it makes sense to sample that more often. And there is tons of work going on to this day. This is sort of where the active state-of-the-art of graphics rendering is, how you optimize this path tracing to be more efficient in different cases. But it is always then you're making your approximations on what you want to do, because you can make, like, the problem with this is if you have, if you're biased and you trace specifically to certain lights, there could be combinations of surfaces here. Like you might have a surface here which is slightly emissive, and if you wind up hitting that because you were tracing towards the light, that's going to get overrepresented based on, versus something that's over here that wasn't in the direction of one of the lights. But this approach, it pretty much works. We do, like for the baking in IdTech 5, we have a very primitive lighting solution because even though we do it offline, we have to, the surface area of one of the maps in Rage is about as much as the pixels that go into a feature film, and we have turnaround time, so clearly we can't do these billions of ray traces for every, what would be a frame of that. We have to keep these down to some credible amount of time. So what we do is when we're rasterizing a surface, we don't even have the viewer at all. We're doing a view-independent approach for the global illumination. And then again, the terminology is problematic because we have radiosity as terminology in a lot of places as a synonym for global illumination. And technically it's not. It shouldn't be that way. I mean, we have a visualizer called Rad Preview, even though it does not do a matrix calculation for radiosity at all. It's, it is based on this more of a tracing approach. So we get our surfaces, we look at all the lights that we think should be affecting us, we trace to them to get our shadows and sample them to make soft shadows. In fact, that's another important thing. The way you get a soft shadow is if you've got a surface and you've got an object that's going to cast a shadow. If you had a point light source, so it was nothing but a teeny tiny point that all the energy came out of, then you would have a hard shadow edge. It would look like Doom 3, where you've got fully illuminated and then fully shadowed. In reality, there's no such thing as a point light source, and this is an important thing to realize. Everything, even if you look at a light bulb, a dangling incandescent light bulb, the photons are actually coming out not off of a point, but off of the little zigzaggy filament that's inside that. It has an area, and the photons come off distributed from that area. Now, the sharpness of a shadow depends on the ratio of the area of that emitter to the distance that it's going across. When you have a great big broad fluorescent light assembly, and you've got a small occluder here, everything is going to be lit to some degree. So in this case, you might have only the very smallest area there that would be solid, completely shadowed. But as you move over, you start to be able to see part of the light. So it gets brighter and brighter until you get to the point over here where you can see the entire light emitter. So we have, to get the soft shadows in Rages, so like if you looked at the earlier Quakes, there were soft shadows in there, but they weren't a matter of calculating soft shadows. They were because we made a hard shadow calculation and then we interpolated between it, which is why you got kind of the blurry stair-steppy edges there. For Tech 5, we actually send a number of shadow samples, and this is one of those things that gets into performance trade-offs where if a designer sets a very large area for a light source, then you'll have a very broad area of changing shadow resolutions, and if you only put 16 tests to it, that means you only have the possibility of 16 bands of different lighting, and that's in the best case if it comes out.
I don't know what it is. I'm just like not feeling it today.